Hello and welcome to our CS506 final project presentation, exploring the impact of worsening weather on the U.S. aviation industry. We are excited to share our findings with you and hope you enjoy. In this presentation, we will give an overview of our project by first describing our data preparation and exploration process. We will then review how we established our argument before creating a prediction model and involving NOAA's supported climate data. Finally, we will discuss our conclusions with the support of our findings. Now we will give a brief project description. For our final project, we explored flight performance and weather conditions using data sourced from Kaggle and climate change data from NOAA. Our analysis focuses on how differing weather types, their severity, and geographic locations influence delay frequency and duration. We took great interest in examining how increasingly extreme weather patterns driven by the climate crisis could change the resilience of the American aviation industry, potentially making air travel more unpredictable and difficult in the years to come. Now we will discuss our data preparation and exploration.
Before beginning our model, we first had to merge our airport, weather, and flight datasets. This produced a dataset with weather events linked to both origin and destination airports for the relevant dates and times. After this, we started selecting relevant features, only keeping features that fit into the following three categories: flight timing and identification, delay details, and weather information. We then had to format the remaining data to be handled properly by our model, changing date-time formats to HHMM, filling in any missing values, and encoding categorical features using a label encoder. Finally, we split our data into training data and two test sets, making sure to avoid COVID data that could skew our results. So our training data set was January 2019 to March 2020, and January 2021 to June 2022. And our testing data was two identical sets of July 2022 to June 2023.
In order to have more information about the weather patterns and the weather trends at US airports, we decided to do some analysis solely on the weather dataset we had. We first handled the missing values and pre-processed some data, and then in order to see the weather patterns, we decided to do some kind of clustering. So we first used the elbow method to decide on the number of clusters we wanted to use, and then cluster the US airports based on their weather patterns with using k-means plus plus with k equals to 4. And then we achieved these 4 clusters. When we look at the clusters themselves, we see that the cluster 2 experiences very high snow and fog and like moderate rain, where cluster 3 is mainly very rainy and has little fog. The difference between the cluster 1 and cluster 3 is that cluster 3 experiences precipitation much more than cluster 1, with little bit less snow, and cluster 0 experiences the most storm out of all the clusters. In order to have some more idea about the weather trends for each cluster, we decided to plot the total duration and average severity from 2016 to 2022. Then we used linear regression to have a more clear understanding of the trends throughout the years, which we will get into more detail in the slides to come. We see that fog has more duration and severity in almost every cluster, and each cluster also have characteristic trends, like where cluster 0 and 3 have clearly much more storm events compared to the previous years. These results signal an increase in more persistent severe weather and support our argument even more.
Now we will discuss how we established our argument through correlation, multivariable linear regression, and hypothesis testing. In our establishing argument for a correlation, we found an R value of 0.3119 between average weather severity and average delay. This indicates a moderate positive linear relationship, meaning as weather severity increases, arrival delays increase as well. Although this isn't a strong correlation, it is still statistically significant and correctly implies other factors like air traffic congestion, airline schedules, mechanical issues, and airport infrastructure are also likely to influence delays.
Here we can see a plot of the average delay time in minutes against average weather severity.
Here you can see the results of a multivariable linear regression predicting delays. This model used predictor variables of severity and precipitation. For each step up in severity category, we observed an average increase of approximately 18 minutes in flight delays across the entire dataset. Additionally, we found that for each inch of increase in precipitation, delays rise about 8 minutes. This finding is particularly significant given the scale used for severity, as it suggests that an increase in weather severity could lead to even more substantial delays, raising concerns about the future resilience of the aviation industry. Under analysis of our multivariable linear regression model, we observed a p-value of about 0. We formalized this as a hypothesis test, and with a significant value of 0.05, we were able to establish strong evidence to reject the null hypothesis and conclude that it is very likely weather severity impacts delays within our dataset.
From the regression lines we got from our clusterings, we extracted the ones which had significant p-values. From them, we see that precipitation is growing alongside fog lasting longer and being more severe. We also have significant evidence that rains becomes a little bit more severe over time.
Now we will discuss how we used climate data as a tool within our prediction model.
We wanted to make sure that we were augmenting our data according to real scientific results and not just picking numbers out of thin air. So we found several papers on the effects of climate change on North American weather patterns over the coming 10 to 100 years. The main figures that we turned up told us that we should expect a 10% increase in precipitation volume, an additional 2% increase on peak rainfall days, and a 1.02 times multiplicative factor to take into account the increased frequency at which weather events will be occurring.
To forecast the impact of worsening weather on air travel, we developed a two-part prediction model. Our approach uses machine learning models trained on historical data to predict across diverse weather scenarios and time periods.
We trained the XGBoost regressor to predict the delay due to weather conditions. As our training dataset, we used flights which were delayed due to weather, and as the key features of this model, we used the details of the weather events at the origin and destination airports. We were able to get a respectable R-squared of 0.7.
Then we trained a logistic regressor prediction model. As our training dataset, we used flights which were delayed and canceled due to weather and used the same features as the XGBoost regressor. After fine-tuning and testing, we were able to achieve a balanced F1 score of 0.71.
After both our models were trained, we decided to augment the testing data with our predictions for the future concerning the climate change, and then redid our predictions. And we experienced an increase of cancellation rate around 0.3%, and we saw an increase in the mean delay around 4.5 minutes.
This is our conclusion.
Our findings have indicated that climate change-driven increases in precipitation and severe weather are expected to worsen air travel disruption. Simulated projections over the next 10 years show a rise in cancellation rates of about 0.3% and a measurable increase in average delay per flight of 4 to 5 minutes. While these figures may seem inconsequential, it's important to remember that we are working with an incredibly large data set, and even a 0.3% increase in cancellation rates and a 4 to 5 minute increase in average delay per flights really add up when you take into account the number of flights that traverse the continental US every single day.
We hope you enjoyed our presentation. For a better look at our project, feel free to check out our GitHub repository at the link found on this slide. Thank you, and we hope you enjoyed our presentation.